In this video, we're going to talk about the effect of lone pairs on molecular geometry. I'm going to start with the example of ammonia. So ammonia is NH3. If I draw out Slewitt's dot structure, ammonia has 4 electron domains. We have 3 bonding domains and 1 non-bonding domain. It's the non-bonding domain that we're concerned about today. So if we consider lone pairs, we're actually going to take a look at how they exert a greater repulsion on the shape. This results in a smaller bond angle because the greater repulsion is actually pushing the bonds together. It's because unlike the bonded electrons that have nuclei to balance them out, non-bonded electrons or lone pairs don't have anything to balance them out and therefore can exert more repulsion. Let's take a look at how that affects the molecular geometry. If I have one lone pair in a molecule with 4 bonding domains, that's going to result in a bond angle of 107 degrees. So in a molecule with 4 bonding domains, I would expect a tetrahedral shape with a bond angle of 109.5. Instead, we get 107. So you can see how this bond angle is smaller. We now have a new bond shape to refer to, which is trigonal pyramidal. So if I have 4 bonding domains and 1 lone pair, that's going to result in what we call a trigonal pyramidal shape. So let's take a look at what happens if I have 2 lone pairs. 2 lone pairs is actually the example we see in water. Water has 4 bonding domains, 1, 2, 3, 4. And by bonding domains, I mean electron domains because 2 of them are non-bonding domains, i.e. lone pairs. If I draw the structure for them, you're going to see that we have 2 bonds that are pushed together to a 104.5 degrees. That is what we call bent. So the 2 new shapes, instead of tetrahedral, that can happen at 4 electron domains, are trigonal pyramidal and bent. Now I'm going to go through the molecular geometry if we have 5 electron domains. So 5 electron domains with no lone pairs results in trigonal bipyramidal. One example of that is phosphorus pentachloride. So if I have 1 lone pair that I add to that mix, I'm going to end up with what is called a seesaw shape. The seesaw shape is represented by, in this case, a sulfur tetrafluoride, and you can see the Lewis structure for it here. So we end up with one little thing that comes down here, and then these 3 that are going around the outside, kind of like a trigonal planar molecule. Next up, we have T-shape. We get T-shape when you have 2 lone pairs. Our example for this is bromine trifluoride, and this is our Lewis dot structure for bromine trifluoride. The angles on this are going to be less than 90 degrees. So you would think T-shape would be 90 degrees because that's what the T-shape is, but because of the repulsive force of the non-bonded electrons, they actually get pushed together more so than that. Our last shape is 3 lone pairs, and this ends up being linear. So those 3 lone pairs form what is kind of a trigonal planar shape around the xenon, and you get 2 fluorines that are on the outside of the xenon. This does end up being 180 degrees because the electrons form kind of a perfect trigonal planar shape in the center of the molecule. Let's talk about what happens when I have 6 electron domains. Traditionally, when you have 6 electron domains and they are all bonded, we call this octahedral. So you can see an example here, and the bond angle for octahedral is 90 degrees. Now, if I have 1 lone pairs, this is going to form what's called a square pyramidal bond angle. You can see that these bond angles are going to be less than 90 degrees. And the square pyramidal is going to result in one of those kind of antenna kind of shaped bonds turning into a lone pair. Then our last shape for today is if I have two lone pairs in a 6-electron domain molecule. This forms a square pyramidal shape. You can see an example over here, and the bond angle for square pyramidal is 90 degrees because the two electrons kind of form our two antennae looking things on the outside, and then the 4 bonded atoms form a perfect square around the central atom, which in this case is xenon. Lastly, we are going to talk about multiple central atoms. Sometimes you'll run into molecules that are larger than 4 or 6 molecules, in which case you're going to have multiple central atoms. So I'm going to talk about this example here, which is methanol. Methanol is going to have carbon bonded to oxygen, and then the hydrogens placed around the outside. So what you can see here is we actually have 2 central atoms. The carbon has 4 domains around it, and the oxygen has 4 domains around it. So what we do is we determine 2 shapes. One shape around the carbon is the central atom, and another shape around the oxygen is the central atom. So in those 4 domains, all of the carbon's domains are bonding domains. This is going to result in a tetrahedral shape. Around the 4 domains of the oxygen, 2 of them are non-bonding domains. So this is going to result in a bent shape. My final shape or Lewis structure or drawing is going to look like this. This is not a Lewis structure. And I want to show you something here. So do you see how I've used these kind of wedge-looking things? They're telling me the shape in terms of something that is not parallel to the page. So if I ever have an atom that is going into the page, I can use these dashed lines in a kind of wedge shape. If I ever have an atom that is going out of the page, I use a solid wedge to represent that. And everything else that is in the plane of the page is going to use a line. So you can see here that this is the carbon, here is the bottom of my tetrahedral shape, and this is the top of the tetrahedral shape, where one is going in and the other is coming out. And this bond angle is going to be 109.5, approximately. Then we have the oxygen, and I've represented our 2 electrons in kind of electron clouds here, just so you can see where those domains are pushing the shape. And then we'll have the 4.5 degrees that you have in a traditional bent molecule. This is an approximation. It's going to change for each molecule, but we know that because it's a bent shape, because there are 2 non-bonding domains, it has to be less than 109.5 for certain. In this video, we've added 3 new ideas. 1, that lone pairs have a larger repulsion. 2, we've learned some new shapes that are results of lone pair repulsion. And 3, we've learned how to do things with multiple central atoms, which is really just going to result in multiple shapes. Good work.